I was interested in math, and when I was a kid, I told my dad I wanted to be a mathematician, and he said, "You can't be a mathematician, you have to be an engineer. Nobody gets a job as a mathematician." So that got me pointed toward engineering. And then I started engineering in college and knew that there was a good match between my interest in math and electrical and computer engineering. And I was interested in computers and programming. So that took me toward electrical and computer engineering. I don't quite go back as far as punch cards, but it's really amazing the how things have changed since I started. I started when we all worked on mainframe computers and we had dumb terminals that we sat and typed at. And it evolved into the PC generation and having PCs and personal computers and laptops connected to servers to now doing so much on personal computers and having the power that many orders of magnitude of the power that we used to have in a mainframe computer now in our phone. And so it's just a totally different world than when I started. And I've been lucky to see all that evolution from ISI, where we're always doing leading edge things. I'm division director for computational systems and technology. So I lead the research that we do in computational platforms from embedded computing to high performance computing, including quantum computing. And then I also provide leadership for the Institute as a whole, involved in our DEI activities. I still do research. It's an interesting combination. I'm in meetings most of every day, but a variety of meetings from research, working with students, working with other researchers at ISI, working with administrators, working with people on campus. So lots of different things. I really haven't navigated the policy part of it until recently. I have started getting engaged with the USC Federal Relations group recently, but I haven't done that throughout my career. But we have interacted a lot with sponsors, and so people who are not necessarily as deep into the particular field we're in, but people who can represent our interests to the people who control the money and helping them understand how to tell a story and what it is that's important about what we're doing has been an interesting part of my career. And we've also had lots of collaboration in my whole career at ISI. I've been very lucky to work with lots of interesting people from other academic groups to defense contractors and other sorts of industry people. Everything we work on has some sort of connection to defense because almost all of our funding comes from the defense world. But anything that's computing related that's useful to defense is also interesting to somebody in the commercial world. So I'd say it's almost all dual use in one way or another. An example of something that the first project I started on when I started ISI was called adaptive computing at the time. It's making use of field programmable gate arrays or FPGAs in defense applications. Now FPGAs, at the time it was sort of a radical idea that we were using FPGAs for computation instead of just for sort of utility glue logic inside other circuits. But since then, FPGAs have been commonly used as accelerators. Intel bought one of the big FPGA companies, and they're now used, for example, Microsoft uses them to do Bing searches more efficiently. They're hard to program. It took the skill set of a hardware design engineer instead of a software programmer to program an FPGA. And hardware design engineers are much more rare than software programmers. And so it wasn't often worth the effort for somebody to program something like an FPGA to accelerate an application. And it was hard to integrate them into systems. But those are problems, both hardware integration and software development, that we've been working over the last 25 years at ISI, and it's now to the point where it can be used for many applications. I've never been bored at ISI. I've always found new things to work on. I've always had good people to work with. I've always felt I've had the chance to make a difference at ISI. And I'm invested in ISI. I want to finish my career at ISI. I want to leave ISI a better place than I joined it. ISI can be a competitive environment. And sometimes that can cut both ways. It's what has made us innovative, but it can make it hard for some people to be integrated into ISI. And so we've been thinking a lot recently about how to adapt our culture so that we're more inclusive and that we can be a thriving home for a wider variety of researchers. The ideal ISIer is somebody who wants to make an impact on the world. The fact that we have full-time research staff and a mix of staff and faculty um, allows us to build real prototypes, and that allows us to have an impact on the world that not all academic groups can have. My research is on software for heterogeneous computing. We build software to manage resources and run computing efficiently for edge computing. Edge computing is pushing computing toward small devices that are put in the field. So resource-constrained devices that might run on battery-powered. Examples are computing that we have in cars or aerial platforms or IoT devices. All of those edge devices are collecting data, and not all of that data can go back to a cloud because you're limited in the communication that goes from the edge back to the data centers. And so the more computing you can do at the edge, the more sophisticated use you can make of that data. Edge computing and embedded computing can help people who are experiencing disabilities and can provide information where they need it and not just when they're sitting at a computer. And so we could imagine edge computing could make a big difference in that kind of world. For example, something's embedded and I'm interacting with my environment, and my embedded camera is looking at my environment, giving me information about what I'm seeing as it's happening. And not just labeling what things are, but is something a threat, or should I remember your name, or what's your background, or what should I remember that we discussed before? And so you could imagine that having either positive or negative implications. It hasn't always been called edge computing. We've been doing embedded computing for decades, but edge computing has become a term that we've used over the last 10 years, and it's just gotten more and more important as we've adopted IoT and put more autonomy into more different devices, and smartphones are another good example. It's easier and cheaper, but the resources that you have are less powerful than what you have in the cloud, for example, and so efficient use of those resources is important so that you can do as much processing as you can in the limited resources you have on that platform. The holy grail is to be able to do processing as data comes in on an edge device and to turn that data into information that a user can use, and to do it safely and securely so that the user can trust that their data is being protected. In order to get the processing efficiency we need to take advantage of heterogeneous processing resources, so specialized computing devices that are good at different tasks. And to manage those heterogeneous devices takes effort on the part of the software developer, and we want to reduce that effort. AI is infused everywhere these days. And for my group, it's relevant in two ways. Adopting AI as a technology inside our systems is important. So for example, I've talked about managing resources, and we can manage resources using AI and deep learning techniques to manage those resources better. And then the other way AI is important is it's important as an application. So if I'm building computing systems that will run applications more efficiently, what kind of applications are they going to run? Well, the kind of applications people are running are AI. Or if you're putting an edge-based system into an environment and it's collecting data, how do you want to process that data and turn it into information? You use AI and deep learning. So those are the kinds of applications we're looking at. Quantum is in a whole different arena. Quantum is not directly relevant to edge computing. Quantum takes, I don't know that I have this number right, but quantum takes kilowatts of energy to bring the temperature down to the temperature that you need to operate a quantum device. So a quantum computer is on the scale of a room. But there are certain problems that we project quantum computers will be able to do that conventional computers can't do at all today, or won't be able to do in the future. Quantum computing at ISI, we have a theory group that's investigating different models for quantum computing and looking for problems at which quantum can be shown to outperform conventional computing. And we're working on technologies including both quantum annealing, as exemplified by the D-Wave system that we have at ISI and that we just upgraded, but we've had for 10 years in our quantum computing center, to gate-based quantum computing model, which is the one that's known for factoring, on which Shor's algorithm has been demonstrated. Examples of the kinds of applications that we're looking at for quantum computing include the simulation of quantum systems. So quantum physics is what rules physical systems at the smallest scales, and understanding how materials and other physical phenomena behave at the quantum level is an important problem for things like designing new materials. And so we're looking at actually using quantum computers to simulate those quantum effects. We're also looking at optimization problems. So any sort of optimization problem where you're trying to figure out the most efficient way to do something, whether it's routing trucks or airplanes from one place to another, packages, any sort of optimization problem is something that we're looking at doing on quantum annealing platforms. And we're also looking at things like fault detection in logic circuits and microelectronics on quantum computers. The greatest potential for impact at ISI is to bring together researchers from so many different areas that can work together to build new things that a more specialized single smaller group wouldn't have been able to come up with, and to be a home for a diverse set of researchers that can all contribute to those ideas and build things that nobody else could. We build systems that are more sophisticated than a smaller academic research could build, but more creative and more toward the leading edge than an industrial research lab or a defense contractor would typically build. So we're in that sweet spot in between. And so we can show the promise of things that are kind of further out than most people can. The impact on society for my group is often indirect because we're building the computing platform, not necessarily the application that is more directly related to the impact. But on the other hand, by putting something in a more efficient platform, it does allow us to change the world. Having the compute capability that you have on an iPhone in a data center doesn't have the same impact on the world as having it in your hand. And so the efficiency of computing platforms has made a big difference in the world and will continue to have a big impact.